the only way that you can really debug something like that is to look at the physics. It's like, okay, this term is large, and my engineering tuition tells me that like that's the temperature. Well, it's too big. It's physically unrealistic. Well, what's the temperature related to? Well, maybe it's related to the specific heat. And so like all of these engineering aspects allow you to break down and look at the problem and then focus in on a particular aspect of it.
Welcome to CFD for Industry. I'm Cade Beck, and I'm your host. This episode is brought to you by Azore CFD, the software created by engineers for engineers. I encourage you to give Azore CFD a try. Azore allows you to customize your workflow without killing your budget. Their pricing options fit both small and large operations. All packages have the backing of high-performance computing, parallel processing, and built-in tools for setting up a run and post-processing results. Visit AzoreCFD.com to start your free 30-day trial today. In today's episode, I'll be interviewing Dr. Jeff Franklin. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. Thank you so much for joining the show today, Jeff. I am just thrilled to talk with you. And before we jump into the good questions that we've got today, could you give us a brief introduction of what you're doing now and what your role is with Azore and Airflow Sciences?
Well, I work at Airflow Sciences, and Airflow Sciences is kind of a consulting company. We're split into several divisions. All of those divisions are really focused on fluid mechanics problems, and they're really applied to heat transfer problems. And the company is divided into several different divisions. We have a numerical side where we help people with consulting by running CFD jobs. We have a testing group that goes out and does measurements. We have a lab facility that, if you want to have something tested in-house, or we build physical models, and we also build testing equipment. And my role there is I do a lot of advising for complex CFD jobs, as well as I am the primary author of Azore, and that's a company that we use that houses Azore and the software associated with that, which Airflow Sciences uses for most of their consulting work.
Excellent. Thank you. And we'll get into this in much more detail throughout the discussion today, but
Right.
that's a nice preview for us. So coming right to it, when did you start this project that became Azore?
When I started working on this really stems back to when I was in college. When I was working on my master's, I actually got a job, like a graduate research job, where I was using a software package called Fluent to run some CFD jobs. And while I was working on that, I was also working with a professor who was interested in doing modeling of like the condensation process for a solar power. And so that had like round pipes that we wanted to look at in terms of the geometry. And I was using Fluent. And at the time, Fluent was all fully Cartesian based, and so like a round circle didn't lend itself very well to that shape, the Cartesian grid. And so I said, well, I'd like to use an unstructured grid. And so I started looking into other methods, and I lit upon the finite element method, which allows triangular elements. And so then that kind of nicely fits within modeling the geometry of a tube. And so that kind of led me, well, okay, I want to be able to do that. So, well, how hard could it be? Maybe I would just write a solver, a finite element based solver, and look at the flow field inside this chamber for the condensation and evaporation process for solar power. And so that's kind of like the premise. And I started working on it. Like, okay, how hard it could it be? And I started writing the solver, and like, okay, well, I read in a mesh. Well, actually I got to solve a linear system. Well, now I need a linear solver. So I go and like, well, I look, I figure out how does a linear solver work? Oh, okay, I need to do this. And so it just kind of rotated and moved on from there. But that's really the premise of where I really got interested in CFD and the numerical methods. And then it kind of went from there. So I had that. And then I went forward and went to other things.
Yeah, just maybe one more follow-up question with that I want to emphasize is this really started as you had a problem that the existing tool that you had access to didn't do the job as well as you like. So you just went out searching for, well, can I do it a different way? And that was the start of this. It was just a natural sequence of I need to solve a problem. And it was maybe we could say problem driven of I need a better tool
Yep.
that
Yep.
fits my problem. I
Yeah,
think that's
exactly. Yeah. Because I needed a round geometry and the Cartesian. I mean, you can approximate it with stair steps, but
yeah,
I wanted something better than that.
yeah, yeah. I just think that's really important. I think a lot of times, especially as a lot of the conversations I have that people forget the value of CFD is helping us solve problems. In and of itself, as a standalone entity, there's only so much use to it in maybe training and educational purposes, but it's to help us solve problems and fix things and design things better. So I just think that's an interesting thing to point out that that was the genesis of the project. So, if you were to estimate, right? So maybe walk us through the next steps, right? You used it later on and you continued to add through it. So maybe walk us through the next few steps of how you continued to build on the existing finite element solver you developed.
So, like, I had this finite element solver, and I basically solved a laminar flow field, and it was a coupled solver. So I had all of the cross terms and everything, and I started looking at that. And then I got a job at Airflow Sciences out of college, and I started looking at much more complex problems. And I started working with another flow solver, and it was like a tank car based one. It was called Viscous, and that solver kind of stemmed from Suez Patankar's Compact One. And that was a staggered mesh, but it was control volume based. And I was like, what is this control volume based method? And how does it relate to finite elements? And so then I started realizing, oh, there are different ways to solve a fluid flow problem. And I could really see the benefits of the control volume approach compared to the finite element approach at that time. And so then I was like, well, actually, I kind of have a little bit of infrastructure for reading a mesh in. I have a linear solver. So, well, the natural progression is, well, because I'm like curious, like, what happens if I solve this using a control volume method? And I already have a lot of the infrastructure. What if I kind of explored that? I'm kind of interested. A lot of the progression of this is really kind of like, well, what would happen? I kind of want to know about that. How can I learn about it? Well, a good way to do it is to try to implement it. Read about the methods. Say, oh, okay, actually a control volume method looks like this. What if I implement it? What am I going to learn from it? And so I started doing that. That was kind of the next step toward it. And that really kind of spiraled into, okay, I really want unstructured meshes. And that right around that time, and that was in the late 90s, I was like, well, a control volume is really kind of just a container of surfaces. Why should I limit myself to like a square? And so I started investigating, well, what if you use a polyhedral mesh for that? And it's like, well, okay, I can't really build a polyhedral mesh. There was no such thing out there. I mean, I could get a tetrahedral mesh volumetrically in 3D, but I couldn't get it. But I was like, don't worry about it. I'm sure somebody will write a polyhedral uh, mesh generator in the future. I'll just focus on being able to solve a polyhedral mesh. And so I started developing algorithms and looking at methods focused around, a control volume technique that is focused on polyhedral cells. Even then, long before it became popular.
Yeah. So, coming back maybe a little bit, in your training in your undergrad or your master's, did you have any formal coursework in CFD per se?
No, actually, I didn't
Okay.
have any. I had my first exposure was I got a job to run some simulations using Fluent.
Okay.
And I didn't even know what Fluent was, and and interestingly enough, even today you have that control where you type in method. It was the same then. That, type in methods, read a file. A lot of that was the same, but I had no formal training. The only real training I had is I took a graphics class on computer programming, which is very handy, I tell you, because graphics deals a lot with geometry. And like we were doing things back then about you draw a line across the screen, and drawing a line across the screen, you were coloring each dot where it went across the screen when you were drawing. You didn't have like some of the wonderful libraries that we have for rendering things on screens. And that was all, and that was kind of my first exposure to the C programming language there.
Okay. Yeah, that's great. I don't think I realized that till just now that you never had any formal CFD training. So that's makes it even more impressive. How many hours would you estimate you spent on this development project? Right, it started as a master's project, and then you took it farther. Then you eventually used it during your PhD program as well when you went back. Right?
Yep, exactly, yeah. I so, like, I was doing this kind of as a part-time thing, I wasn't involved, like, I was working for Airflow Sciences in my day job, I'm doing consulting jobs, I'm running CFD simulations, I'm going out on test trips, I'm doing all of the things that somebody in the fluid mechanics and heat transfer consulting business would do, but kind of in the evenings and on the weekends, or I go on a vacation, or I just really felt, interested in learning about this CFD. So I'd spend a couple of hours in the evening, maybe 3 or 4 on the weekends, and so I probably put 1,000 hours a year in, roughly speaking, and it was over a long period of time, like 15 years before it all really started coming together.
Were there ever moments that you were just so frustrated you want to drop it? Right, that's a long time to be investing in learning. Obviously, you were interested in it, and it complemented the work you were doing nicely with Airflow Sciences, right? And the understanding of what's going on in these solvers. But were there ever times where you just felt like, I'm done, I'm dropping it, and maybe you took a long break from it, or
No, I mean, like, for that period of time, it wasn't like if I was really trying to write a solver and be successful and be done with it, and that was my goal, I'm sure I would have gotten frustrated. But it was all the whole time, most of that period was a learning process.
yeah,
And it's like, it was an opportunity to learn. It's like, oh, I need to find the volume of a polyhedral cell. Well, how do you do that? Well, you do this or you do that. Oh, I need a simple algorithm. How do I connect the continuity equation with the momentum equation? What does that look like? And some of my, the time would be spent deriving. Some of it would be like reading a bunch of papers. I mean, you wanted to implement a simple algorithm. You can open any textbook and look and say, okay, these are all the equations. How hard can it be? You type it up, run it. And like what I learned a lot was it's like there are small details that are left out of almost every derivation. And those details, when you go to implement it and have it work very reliably, are super important. But it really was educated because I would implement something. I'd be like, oh, yeah, it's not working very well. Oh, but maybe, oh, I see. Like maybe this term is growing where it shouldn't have. Why is it growing? Well, then you go back and look at it. It's like, well, actually, that was never mentioned in this paper. That term was not even there. But if you go back and derive everything from first principles, you realize, well, there are some few terms. And then maybe those terms in a particular problem wouldn't be important. But when you use it for a wide array of things, I would discover that maybe those terms become important.
yeah. Is there a specific example that you can give that you remember of maybe one of those things where a critical detail was left out and the effect that it had on the problem? Or
Well, I mean, I think putting together the simple algorithm was probably the simple algorithm for a collocated grid was probably the most challenging.
okay,
I was like, you break open a textbook and I would write one up and it wouldn't work. It just wouldn't work for one reason or another. And then, I would scratch on the back of an envelope and say, oh, I forgot that. And then I would try it and it wouldn't work. And it would, so, and like, in order to get the simple algorithm to work reliably for a wide range of things, I ended up deriving that in great, great detail, all from first principles, storing every single term. And I have a very large LaTeX document that has everything derived out to the very last algebraic line that needs to be programmed. And that process was iterative as well, because there's a lot of algebra involved there in putting that together. And I would program something up and I would basically program it up to discover that I had an error in my algebra. And then like, oh my gosh, why is that growing? That term shouldn't be growing. And then you go back and like, oh, yep, I got an algebra error here somewhere. I got to fix that. So it was kind of an iterative process between deriving the relationships and implementing them as well.
yeah, you just reminded me in my undergrad, my Calc 2 teacher, her name was Miss Yi, and she was so
Hmm.
kind. But on the exams, I kept getting lower grades than I thought I deserved. And as I went to talk with her about the exam and my grade, she was like, "Your calculus is fine, but your algebra errors are horrible." And it just reminded me, as you said, algebra error. That was one of my significant shortcomings in Calc 2 was just making algebra mistakes. And yeah, it's easy
Yeah.
when you're going through. I can't even imagine going through deriving that from first principles. But you bring up another point that I wanted to touch on. You documented in LaTeX. When did you
Yep.
start doing that? Because I find um, the the older I get, the slower I go at approaching problems. I think, and I'm still not as steady as I'd like to be, but it's enticing. I think early on to race through to the end and to skip some of the documentation. It feels slow, but with your benefit of experience, how beneficial has that been to have this documented process?
Oh, it's absolutely. I mean, I have done it so many times where I just scribble it on an envelope and put it together, and like that just typically does not go well. There is always something, and it is worth the investment. And I early on, like I started at LaTeX, there's a learning curve to using LaTeX for sure.
Yeah.
It's a very powerful tool, and I'm of the age where we didn't have many other options, but I was using there was a tool called Star Office that evolved into LibreOffice, and I was using that to do my derivations, to store them. And it got to the point where I had all of these really complicated equations in there, and it was like megabytes. The document itself was megabytes, and it would take forever to update. And I finally got to the point where like, this is intractable. I can't even deal with it. So I ended up transcribing everything out of Star Office into LaTeX. And the LaTeX document is so small in comparison, but you need to learn LaTeX, of course.
Yeah.
And I'm familiar with programming, and LaTeX is basically a program. You're writing a program, you run it through a compiler, and it gives you a document. And so that, I guess, kind of fits with some of my background and the things that I'm familiar with. And I still use LaTeX to this day, even for me writing reports. Like I need a table, in one of my reports, and cutting the, numbers out of a spreadsheet and pasting them into a document. Like I just run it through a script, kick out a LaTeX document, and I'm done.
That's awesome. I was introduced to LaTeX during my master. Well, no, it was after. I wished I was introduced to it during my master's and getting the formatting of the thesis. It was a nightmare doing it with Word. And so
Mhm.
for my PhD dissertation, I had to get special permission to use the electrical engineering department's uh, format because they kept giving me flack in my department of using LaTeX. And I am
Uh-huh.
so glad that I took the time to learn it and it made things so much easier. So, for those of you that haven't tried LaTeX and you're looking at an easy way to format and do mathematical documentation, it is an excellent, excellent choice.
Yeah, I mean, I use it for my derivations and some of it, like even like all of the algebra, just to be able to see it on the screen. And then like when you're doing derivations, you have your whole equation and then you copy it and you're doing the next step of algebra. You can just do it, and it's actually faster than writing it down, I find.
Yeah. Yeah. There's definitely some huge savings once the initial learning curve, like you talked about,
Yes.
is
Yeah.
overcome. It's different. So that's fantastic. Um, so how did you go about getting feedback on the code? Did you just do benchmark cases or were you using it for maybe some classical problems? Did you share it with colleagues or how did you get feedback on the solver?
So a lot of the problems early on, I just had all manner of benchmark problems. The lid-driven cavity, and I did a bunch of them. The triangular shape, the L shape, all of those different mesh topologies. And then early on, when the internet became more easily accessible, I got access to more test cases. The backward-facing step, and I just started running these various problems and looking at the results. And, that's early on, probably within the first 15 years, there was a lot of that. And it was just me. I would reach out to talk to various people about like if I was having problems, or I would talk to researchers. I spent a lot of time reaching out to researchers. Like I'd be reading a paper
Mm,
and it's not going like I expected. I would reach out to them, you know, back then it was like a phone call. It's like call, and maybe some of them would talk to me. Maybe some of them would just totally ignore me. I mean, even like one of the early times is kind of interesting when I was working on my graduate work in Sacramento, California. I was working on this finite element method and I couldn't figure out what was going on. And I was looking through the book and I noticed that this guy named Phil Gresham, and he worked at Lawrence Livermore National Labs. And I was like, oh my gosh. And I called and talked to him, and he answered the phone. And he's like one of the early researchers. He's done a lot of work with the finite element method. And I called him and he said, and he was only like 2 hours away. And I ended up driving down there and he was super nice. He brought me in, he showed me his group, and we talked about the finite element method for fluid flow, which he was one of the first people to do that. And his group discussed with me, what I was doing and the problem I was solving and how to do it. It was super nice. But like at that time, you really needed some, personal connection because you didn't have the web to just Google it. I mean, accessing technology and information was a lot harder.
So how did you even find their phone numbers?
I just call them, I would just call the main line. So
Okay.
I call Lawrence Livermore National Labs. I want to talk to Phil Gresham. Can I talk to him?
Okay.
Yeah, here's his number.
Wow.
I mean, there's I mean, at this day and age, that is less common
Yeah.
because people are going to answer their phones now.
Yeah. Yeah. No, that's absolutely remarkable. What a
And
neat.
it goes along the line, and I would say, hey, I'm a student at Sac State, stuff like that. And I think
Sure.
that helps, of course. If I
Sure.
was trying to sell him something, he probably would have never talked to me.
Yeah. Yeah. You've got to couch the pitch, right? Of context of why you're reaching out. But I think you bring up a good point though, and this is something I often try to emphasize is that as engineers, we may not think of there's perhaps this negative connotation with networking, right? And reaching out to people and connecting and making meaningful relationships with people. But as you hear these experiences, especially, it's just exploring curiosities with like-minded people and other people who know what they're doing. And so I think there's a huge lesson to be learned here that as people reach out, having done what they could to learn what they were trying to learn and then reach out for help, that is something I feel like we've lost in our day of instant access to everything. And I think that's something that we need to recover, at least in this generation. Um, so at what point did you realize that you could commercialize Azore? Was there ever a point where you're like, wait a minute, this is a fully fledged functioning solver and I could sell this? What was that process like as that evolved?
So the process, basically I developed it. I got to the point where I was able to solve some really interesting problems. And then I started using it on problems at Airflow Sciences. It's like Airflow Sciences is like, hey, you got this solver that's working. Maybe we can use it for a few of our problems. Licensing is expensive sometimes. And if there's another option, maybe we should look into it. And so I started running some of the problems at Airflow Sciences. It's like, oh, let's run this problem. Oh, that worked pretty well. And so and that process took a long time because a lot of times, I learned a lot. I think there's a stage between, like, I had something that worked for a few problems, but there are just, I call it, there's a numerical black magic in a flow solver. And there is a lot of it in order to make it work at an industrial level, at a commercial level. And that process takes a long time to explore and come out. And so that process went along for a while within Airflow Sciences. And it got to the point where, like, hey, we're using this and we're using it very successfully. Why can't other people use it as well? And that was kind of the aha moment. It's like, okay, we're using it. We might as well see if other people could use it too.
Yeah. Um, as you talk about that transition from having a functioning solver to a more generalized solver, right? You tested it on some classical benchmarks. Were those um, developments that you found you needed to make, were they primarily in the physics that needed to be added? Were they in maybe boundary conditions that needed to be added? Or was it just a smorgasbord of a thing here, a thing there to continue fully fleshing out the solver?
Well, I'll use an example. Like, when I was developing the solver, one of the first problems I solved, most people look at the lead driven cavity, right? It's
Mhm.
just a square box like this. Ran that problem, correlated, it worked beautifully. I thought, okay, I'm done. I have a flow solver. And then I got this other case, and it was a triangular shaped cavity. And it's like triangular shape like this, and then you slide the lid. And I was like, oh, okay, I'll try to run that. I tried to run it, wouldn't run. Totally wouldn't run. And it was a triangular. And like, of course, it took a while to figure out. It's like, why was it running? It was diverging. It was completely diverging. And then I realized that down in the corner at the very bottom, you end up with one triangle, essentially. And the mesh that I happened to get, the triangle was not symmetric. It was just a little bit off of symmetric. And so because it wasn't symmetric and the gradients that I was calculating down there were not carefully balanced, the gradient itself kept growing and growing in that corner cell
Okay.
because the algorithm that I had chosen for the gradients in that cell, there was just a little bit of fuzz in there that shouldn't have been there. And so it basically made that problem intractable. And that's what I'm talking about. Like these little teeny details are what are the difference between a solver that runs for a few cases where you get your degree, and one where you have, you know, 300 people throwing all kinds of problems and all kinds of mesh topologies at you, and you could solve every single one of them without a problem.
Yeah, well, and I think this is interesting to point out. I do not know of a single commercial solver that has one principal developer. Like you wrote the GUI, you wrote everything for
Yep.
Azore. And
Yep.
so the man out, like if you were to take Fluent or Star CCM Plus and agglomerate the man hours that have gone into writing of those codes, and that's just a huge effort, like you said, of taking any code to make it a generalized code. And so the fact that you have done this as the single principal developer for Azure is still just astounding to me. It's really remarkable, Jeff. Um, what are perhaps the 2 to 3 most valuable lessons that you've learned from developing Azure that you'd share with listeners?
I think one of the ones that I found useful even to this day is to be able to break down a problem and from an engineering perspective. And simplify it and say, okay, these are the important aspects and these are not. And the reason I bring that up is like debugging a solver. So like there are parts of development that I've done. I did all of the GUI development. Most of the reason I developed the GUI is I needed to look at my results and there was nothing out there. There was no pair view. There was nothing out there to post-process the results. So I had to have something to look at my numbers. So I started developing a post processor simply so I could look at the results. And so the GUI is relatively straightforward. You put something in there, it pops up a box, you type a number in, and it's kind of linear in fashion. Whereas on the solver side, it's a little trickier. Like if something doesn't work in it, like you have a problem, and like these days, you have a problem. You have a model that's 100 million cells or 50 million cells, right? And you're running the job, and after it's been running for a day and a half, it diverges. And you have to ask yourself, well, why? Well, millions of calculations have been made there. There's no way to as a programmer, only as a programmer to look at all of those numbers and sort out which one was wrong. The only way that you can really debug something like that is to look at the physics. It's like, okay, this term is large, and my engineering tuition tells me that like that's the temperature. Well, it's too big. It's physically unrealistic. Well, what's the temperature related to? Well, maybe it's related to the specific heat. And so like all of these engineering aspects allow you to break down and look at the problem and then focus in on a particular aspect of it. And a lot of the problems that I've had to debug over the years are super hard to find. I mean, I have looked at problems for a month or 2 months just to find a problem. And it may end up like the solution may end up being like 3 or 4 characters to fix the problem, like in the code base.
Yeah.
I used to joke with my wife. I'd walk back into my room, at night and like, "Gosh, I found a problem, but it's not the problem."
Mhm. Oh my
So,
goodness.
so anyway, but the point is that that having to debug these things at such minute detail really made me focus on all the little teeny aspects of what a flow solver does, and really what the physics are involved with that. So, like when you're running any commercial package and something doesn't look right, it's like, oh, darn it, the energy equation's not looking good, or my flows are not correct. It's like, oh well, maybe my density's wrong, or maybe what relationship am I using for my density? Maybe I can look at that. So it really provides an invaluable tool for me to be able to parse down a problem from the engineering perspective down to the numbers.
Yeah. It just reminds me, in one of my graduate courses, we were taking a closed conduits class, so pipeline systems, and we were writing a transient solver. And the final project, we incrementally built up to it. And at the end, we had this pipe network and we were calculating the transient as it went through. And we had the pressures, the spike and the negative, right? And at the end, our professor asked, I don't remember exactly the detail, but something to the effect of, okay, what happened? And we all raised our hand. We said, well, the pressure went to this value. And he's like, does that surprise you? And none of us, no one in the class had recognized that it was below vapor pressure. And it was like, this means the pipe imploded. Like, and we didn't connect it to the physics of, we had just been looking at straight numerics. And I don't even remember. It was probably like negative 200 PSI or something, right? Like it's not possible, right? You have to look at the physics. And so it just reminded me of that as you were talking of being able to keep the physics as the lens through which you look for those things is absolutely critical. So, um, were there so breaking down problems, are there other lessons that you think are also really key or that really stand out to you in this development process of building Azure?
Um, I'm trying to think of. I mean, there are certainly very good problems about. I learned a lot about how to program. And that was another thing that I learned a lot about is programming. And because I'm not a computer scientist at all.
Mhm.
And like I would implement an algorithm and it's dirt slow. And it's like, why is it so slow? And then I start digging in and you say, well, actually, I'm moving a lot of data. I need to not do that. And so it really kind of forced me to become a programmer as well, because I had to learn a little bit of computer science. And I'm no computer scientist at all, for sure, but I have learned a lot, and most of it is through hard knocks. It's like, this is slow. And then, of course, there's, you can read, different people doing things like you're designing a linear solver. Lots of people who have designed linear solvers, and there are papers out there that you can read about how to do that. And then, so I would look at those and read them, but like, always, the linear solvers have to be meshed quite nicely with the structures of how you build the linear system together. So like all of the solvers, the linear solvers within Azure mesh very nicely with the data structures of the mesh and how the matrix is put together. So there's no like offloading, like you create a mesh and then you copy it over to a library to solve the linear system. That just becomes intractable and inefficient. Those two you have to have a good data structure in your mesh topology that leads to passing information over to your linear, how you're holding your linear solution as well. So you can pass that information over. So computer science is another thing that I learned a lot
Yeah.
about.
Yeah. This brings me, so this was probably shortly after we met. You ended up sharing a quote with me that you've kept on your at your desk for the last few years. I can't remember how many. And I'll just take the time to read the quote and the adaptation. So this was from GJ Quaderer of Dow Chemical. He said, 4 to 6 weeks in the lab can save you an hour in the library. And you had modified it to read 4 to 6 weeks programming can save you an hour in the library. So is there a particular story that goes with when you found this quote and decided to put it up, or that sums up your experiences? Did you just find it and feel like it captured a sentiment that you wanted to be remembered of?
Oh, well, and like that is One thing, as a consultant, we're posed with many different problems daily, for this problem and that problem. And it's easy to sit down and say, oh, we'll just do it this way, or we'll just do it that way. And we can think, oh, and like a lot of the things that we do at Airflow Sciences is we write custom routines to deal with various physics. And I kind of, this was one of my colleagues. He was like, oh, we'll just do this. And I was like, well, maybe we should do a little bit of research before we just dive in and try a particular numerical method. And this was like, hey, we should do that. And it was always a back and forth. And this quote I found, and I said, this is it. We could throw a method at, a particular problem. And maybe we would get lucky and maybe it would work well, but chances are somebody has looked at this problem before you. And it's better, even if you spend an hour, to see what people have done. And maybe you find nothing and then you can branch out on your own. But if somebody's done a bunch of work on it, it's better to start where they had, or at least learn from them before you kind of launch into your own. And that really stems from, like, we deal with these problems all the time at Airflow Science.
Yeah. So, and you mentioned this a little bit, but I suspect there's a trade-off of spending too much time in the library, right? And not enough time implementing and learning what you're trying to do, because oftentimes what you're trying to do is slightly different, or you need to also keep moving along with industry consulting timelines. It's not like everything can
Mhm.
be turned into a research project, which I understand is not what you're saying.
Yeah.
But just to clarify, did you feel like what things helped you get better at striking that balance? You mentioned an hour is kind of a mark point of let's spend at least a little bit of time exploring and reviewing what's been done. But
hmm
do you find that there's times where you've spent more than that, or
Yeah, as a consultant, a lot of times it's driven by the client's schedule
hmm,
and what they're willing to do. And so sometimes you have a client that they have a problem and it is a big problem and they need a solution very quickly. So you have to really rely on your own experiences to solve that problem. You might have and so then the amount of time that you might spend researching it is low. Other times you may have a client that says, I have a problem. I need a good fix for it. And so then you have some latitude to go out, maybe do a little bit of research, and then provide maybe a very good valued solution to their problem. So I'd say it's very often client driven,
yeah,
in my arena, more than anything
yeah,
in terms of striking that balance.
yeah, that's great. Um, so transitioning a little bit more to Airflow Sciences and Azure specifically, what do you view as the unique advantages of using Azure extensively in your work with Airflow Sciences?
One of the things about Azure, because of the way it evolved, it was evolved and its tools are designed by somebody who's using them every day.
Mm,
And so I have, there's 10 engineers that if something's not working very well, they're standing in my office going, yeah, it shouldn't do this. Or I might be using it going, oh, this is ridiculous. I'm not waiting for this. And it's changed. So the ability to solve engineering problems, I'd say, is Azure's largest strong suit. It is really designed, and the post processor is also designed. It is a very well-shaped processor, and it's designed for extracting information for design purposes, and making reports and having very nice graphics. Those are the really big, strong suits. I mean, of course, it solves all the problems, just like most of the others, that, it gets the right answer. We're all solving the same differential equations, and it solves them all at about the same pace, parallelizes the same. All of those things are the same. But the big, strong suit is that it's designed to be used. It's not designed by computer scientists. I mean, though they do a great job. I'm not saying that but some of them, sometimes they might lose perspective of solving an engineering problem.
But I think that is something that readily stands out to me too, is the fact that no matter how hard you try, I think just the amount of perspective that you have as a user of your own software day in and day out for your company provides insight that I think would be very difficult to obtain any other way as you develop the tools. on the developer side, right? As you switch hats and put on your developer hat. So what do your customers tell you about why they use Azure?
Of just those things. I mean, they like the ease of use. They like to be able, they like its flexibility to work with other, mesh generators, other, the workflows that they might have. It works well with all of those people
Yeah.
as well.
So when when you're looking back on what you've accomplished and your career in developing Azure and your work with airflow sciences, are there common myths or misconceptions that you see as right? You have a lot of opportunity to mentor new engineers and to train them and help them learn CFD and to really understand. So, is there a common myth or misconception that you've encountered with their perceptions about learning CFD?
Yeah. I mean, I even all the people I mentor, it's the whole pipeline. You set up a problem, you kind of characterize the geometry, you mesh it, you run the simulation, and you get the results. And everybody races right through that. And everybody is all about getting the simulation running. And that I feel is probably the worst thing that can happen in running a simulation. The setting up the problem, like when you set up the problem right here, taking some thought about what you're trying to do and what you want the CFD to give you, um, is like probably the most important step in running a CFD simulation. Almost, I mean, if solving any problem of any engineering interest, you know basically what you're looking for. You have a rough estimate of what's going on, what should come out of it. You know how much energy is going to go into it. You know how much flow is coming in and out of it. You should really have those in mind when you set, and it provides a framework for everything else that you do. It provides a framework for the geometry that you want to include. It provides a framework for the mesh density and topology that you want. It provides a framework for the fundamental equations that you're going to solve. And it also provides a framework for what you want to get out of it. Like one of the things that I think is lost by many people is when you're putting together a mesh at Airflow Science, if you want to extract information out of your model, it's very common to just put an arbitrary cutting plane through your mesh topology. And so like that, you're getting interpolated data. So it doesn't necessarily conserve mass at those locations. And so a lot of the things that we do when we put a mesh together, it's like, oh, actually, we know we're going to ask for data at this plane. So we put a mesh, like we put actual mesh topology in there so that it has a surface that is on the mesh line. So like our control volume method, it's going to be honored at that location. And all of the information that we pull out through the GUI is going to be very faithful to all the conservation of mass, conservation of energy. It will all be faithful to all of those things. I guess I'm going to back up and say, uh, always look at the solution itself. Think about whether or not it means something. I have a tendency to say, oh my gosh, what's wrong with that? I'm always looking over my shoulder thinking, what is wrong with this? What have I not set up properly? Or what could have gone wrong? Because, I've encountered many, so don't trust everything. If it looks too good to be true, or if it doesn't look correct, it's probably not.
Yeah. Yeah, that's excellent. Excellent counsel. Another reflective question, I think. What do you and you've given tons of excellent advice throughout the discussion and really appreciate that. But maybe one final question of what do you know now that you wished you would have known when you were starting out in CFD? Is there something that really stands out to you? Or maybe it's not something you've known. Maybe it's a skill or a habit that you've acquired that you wished you would have had when starting out. But what if there was something to sum up your learnings?
I would say like pay attention. I mean, like school is very important and it provides you a good foundation of understanding, conservation of mass, conservation of, all of these things. Having a good foundation of engineering principles, I think, is the thing that sometimes gets lost. I mean, you don't depend on the solver to tell you that you have conservation of mass. That is not something that you should get out of the solver. You should know these things in advance and have a good perspective on them. And I wish that I had done that more in the past than I do now. I mean, I do that very easily now because I've been beaten down so many times, but I was very eager to just go through and say, okay, here's my answer. Let's just go with it, without taking a closer look at it or even developing that capability. I know when I was working at Airflow Sciences, I actually went back and I got a degree in chemical engineering as well. And I went back and I was taking some similar courses that I took before. Like I took a heat transfer class and I was like, my gosh, I got to pay attention this time because when I sat down as an engineering consultant, I realized I kind of maybe understood it when I did the exam. But now that I have to use it out of the framework of that problem, it's a lot harder to apply. So having a good, solid understanding, I was like, I got to pay attention this time because I need to use this tomorrow.
Yeah. And maybe we can dig a little bit deeper here. You've mentioned a lot of these learnings have come from maybe you observing others' learnings and maybe mistakes that they had made. And you mentioned the phrase just again that you've been beat down on maybe not applying things as rigorously. So, what would you say? I guess what I'm saying is a lot of this stuff takes time. It you can't shortcut it. And so the direction that you're headed is more important than the speed, right? That's one of the things I feel like is
Hmm.
implicitly coming out in our conversation that if you're focused on the principles, your workflow's solid and sound and you're applying sound judgment and principles that it will compound over time and you'll reap the benefits of it. But is there an experience that particularly stands out of maybe um, learning, "Oh, yeah, that wasn't the way to approach it," or that wasn't I went too fast or I went too quickly, or
We got we were doing some research, and what we were trying to do is we were looking at boiling heat transfer. So people take gears and they put it in oil and it boils and it, cools the gear and you get the material properties you want in that gear. And we said, okay, we're going to model that. We're going to put together and like, all we're really going to do is we're just going to put, on our surface, we're going to essentially change the wall function there to accommodate the boiling heat transfer. And it'll be simple. But they said, well, we need to know how to change it. And so what we need to do is we need to get a little bit of test data. So what we ended up doing was putting together a research, and we built this rig and we in detail, um, we had a fixture. We would flow oil over the top of basically a heated stamp or like a little pad. And then we had thermocouples in there and we started looking at the boiling heat transfer there and at different regimes and how it worked. And that was very enlightening. And we realized that, oh, like actually, if we heat the oil up and it goes through the different phases of boiling heat transfer where it just heats up the liquid, then maybe a few bubbles form. And then a little bit while later, when you have so much heat flux on the surface, it's completely enveloped in a film boiling is what it's called. And then you have a temperature profile there. But if you start a film boiling and you start slowing down the flow, then that film will collapse on top of it. But what we found was like if you wanted to, we were thinking, okay, we'll just come up with this curve. But what we found when we started experimenting, that it would collapse at a different point in temperature than when it was going up. So it was like some hysteresis there. So coming up with some sort of universal heat transfer relationship there that you could put in mathematically became very tricky. So I guess that was one thing that in my past that I tried to put together and realize, oh my gosh, this is going to be a lot harder than I thought.
yeah. Yeah, and I think that's just part of how it goes though, right? You take a stab at it and then you realize this isn't quite what we thought, and then you adjust and modify and figure something out for an engineering solution, right?
Hmm.
So,
Hmm.
yeah. No, that's excellent. That is excellent. Is there, is there anything else that you'd like to share with listeners? I know we've covered a lot of ground today. and it's been really insightful. Really appreciated your comments. But if there's anything else you'd like to share with listeners or any other final words of wisdom.
I would say the big word of wisdom I would use are like the CFD tools are so powerful today. Like you can make a mesh of something very complex, and with a single click of a button, you can add radiation and all kinds of physics to your problem. And and so you could start with a a problem that's very complex. And I would say start simple first. Look at something. Don't turn on the radiation equation unless you think it's necessary. Don't solve for temperature field unless you think it's necessary. Try to break the problem down and start with something simple in geometry and work to something complicated. Don't go to super complicated and work backwards because it didn't work very well. Because it's very hard to go backwards, and it's super complex. It's time consuming. If you go with a huge mesh and lots of physics, you're going to burn up all kinds of computer time to discover that, like, oh, there's things that I need to learn before I do that. So start simple, I guess, would be my advice.
Yeah. So if someone's interested, thank you. That's excellent, excellent advice. And if someone's interested in trying Azore CFD, you've got a 30-day free trial license, right? And how would they get access to that?
It's right on our website. I would really encourage people to give that a try. And, reach out to me if you have any questions. Of course, we have free trials. We're very eager to have people give it a try. I think we use it very successfully, and I would really like to have other people enjoy the success that we've had with it.
Yeah, that's fantastic. And I can add a link to um, the webpage and your contact information in the show notes here so they can access that. But thank you again so much for your time, Jeff, and we really appreciate it.
Thanks for having me. It's been a pleasure talking with you. You do some great things that I enjoy watching them.
Thank you. Really appreciate it. Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.